All right. So good afternoon. In today's session, we will be looking at the topic of process control management, specifically CPU scheduling. So right off the bat, before we begin, let us contextualize the story so far. We have been looking at computer technologies, specifically hardware and software. So in the last class, we started by looking at a description of the operating system. So we went ahead to define that an operating system is basically a set of software. So it has multiple components working together to control and coordinate all the activities of a computer. We're going to continue with that discussion by looking at specific important uh, aspects or functions of this operating system. One of the things that an operating system does is basically managing memory and managing processes that are actually executing. So if you have a number of programs running on your computer, your operating system is responsible for managing those software. Management here means allocating and deallocating resources. So on my computer, if you take a look at my screen, I have a bunch of applications running. So I have the Microsoft Teams application, then I have my OneNote, my web browser, and I have the PowerPoint software all running. All of these programs will require some type of resources in terms of hardware and in terms of software. And these resources have to be shared. So the operating system's job is to perform this sharing action. So the two main resources, remember, on your computer, let me just jump into OneNote. On your computer right now, you have essentially two primary components like we mentioned. So you have the hardware and the software. So when we talk about resources in this context, most of the resources fall under hardware. So the hardware are the resources. These include input devices, output devices, processing devices, and so on. So storage and communication devices. These are all considered hardware resources. So these are fundamental components that your computer needs to perform the actions it needs to perform. With regards to processor, typically you will have one processor or a set of processors typically on a single chip. So in modern day computers, you will typically have a dual, a quad, or even an octa-core. In my case, I have a 10-core CPU, and it's not uncommon now to have cores of 10, 14, and so on with especially modern day computers. But the idea is the CPU is still considered one super component, even though there are multiple cores. So the way it will work is this processing unit, the CPU, can have a set of cores, but the idea is you can have a number of programs. So let's here say P1, P2, P3, and P4. All of these programs will require some attention of the CPU at some point in time. In other words, the CPU is a resource that they have to share. So if you take a look at my screen right now, I have my Microsoft Teams, my PowerPoint, and my OneNote, as well as my web browser. So that's about 4 applications. And then I have a couple of things also running in the background, my Excel, my Word, my WhatsApp, and so on. So I have a number of applications running. So part of the job of the operating system is to provide each of these applications the resources that they need. So part of the resources are, the first important resource is CPU time. This CPU time is the time spent with the CPU as shown in this example here. Every process needs to go and see the CPU to be fetched, decoded, executed, and stored. The second important resource is memory space. Every open program has to have some place in RAM to actually be stored so that it can be fetched, decoded, and executed. Some processes, some, not all now, might require input-output devices. So imagine if you go to a website and you visit a web page, and on that web page, there's a login form. In order to interact with that login form, you'll need a mouse and a keyboard and a screen. So the mouse and the keyboard are input devices. The screen is an output device that shows you the feed of the form. So that particular process that is running in the web browser, you can call it a login process, requires your CPU time, memory, and input and output devices. So every single process will have a list of things that it requires. What we're going to try and understand today is how does the computer's operating system manage the CPU time? In the next lesson, we will now focus on how it manages memory space. So for today, we're relegating ourselves to how does an operating system maintain and manage the processor to run operations or to run programs as it would. So this topic is called process control management. Specifically, we are going to be looking at CPU scheduling, which is under process control management. So let's go ahead and begin. Can everybody see my presentation screen clearly? Okay. So the learning outcomes for this include, at the end of the lesson, we should be able to define what a process and what a thread is. We should be able to draw and explain something called the process state diagram and the process scheduling diagram. We will also be looking at the aims of why we're doing CPU scheduling as a whole. And we will also try to perform certain calculations relating to the scheduling systems that an operating system would implement. So these are the topics we're going to cover. So let's dive right in. First, we want to begin by defining properly what a process is. So to do that, I'm going to come back here to my OneNote app, and I'm going to illustrate it as follows. So what you want to understand is the term software is the same as the term program and is the same as the term application or app. All these three words mean exactly the same thing. They are files that consist of lines of instructions that are written in a particular programming language, compiled, and then the binary files will just have basically a list of instructions. So it's good to imagine a program as just a set of instructions. For the computer to perform or to run this program, it has to fetch these instructions, load them onto memory, and then give them access to the CPU time. In other words, my CPU, in order to perform the actions or the instructions in this program, we need to fetch the instructions. So what happens is we fetch the instructions line by line. And every time the CPU fetches an instruction, the CPU performs the instruction. So I want you to imagine it like a person in a kitchen trying to cook by following a cooking recipe. The cooking recipe is the instruction file. It tells us what we're going to do. It gives us the instructions. So if it says maybe take egg and flour, put it in a bowl and mix, that's the instruction. I, the human actor now, I'm the processor. I read that instruction, I understand it, then I begin to perform it. So an instruction that has been fetched by the CPU and is being performed transforms into what we call a process. So what is a process? A program instruction in execution. So let's write that down just to be clear. A process is a program instruction in execution. Very simple. So the instruction says do ABC. When the CPU fetches the instruction and starts performing ABC, the CPU is now running the process. In other words, the instruction becomes an action that the CPU performs. In English, we call this a verb. Right now, what am I doing? I am actively sitting down and delivering a lecture. So that is what I'm doing. So the action or the process that I'm doing now is sitting down and delivering a lecture. So the CPU reads an instruction and then performs it. So when it performs it, we use resources. Right now, for me to lecture, here are the resources I need. I need my computer. I need my internet connection. I need my voice. I need my microphone. I need my screen, and so on and so forth. I need my lecture slides and so on. So all of these are the resources that I, as a processor, need in order to deliver a lecture. So also the CPU, for every program it's running, each program will have its own list of resources that it needs that has to be allocated. In today's lesson, we're concentrating on the CPU. Now, every process needs the CPU time because the CPU is what executes the program. And in order to execute the program, the instruction needs some time with the CPU. I want you to think of it this way. If you look at your class timetable, your lecturer, let's say your lecturer is a processor, that lecturer is going to be shared amongst many different intakes and groups and modules. So for example, I teach about 4 or 5 modules. Those 4 or 5 modules that I teach, they all have to share me as a processor. So in order to share me, we have this thing called a timetable that shows when I'm busy, when I'm available, and with who I'm going to be busy. So the CPU scheduling is all about creating a timetable that defines how much time each process spends with the CPU. So we share it equally. So we're going to look deeper into this activity. What you need to understand is everything that has to do with CPU is basically based on time. How much time each process spends with the processor. So a process, we can simply define it as P. And we said that this P requires resources. So these resources include, one, you must have CPU time. That is some time with the CPU. You must have memory space. That is some space on RAM. And then you might have others. So I'll just put ETC here. So these others include input-output devices, network connection, access to files, access to other programs, and so on and so forth. Are all resources that a process might require in order to perform its action. So let's jump back into the slides. So this is what a process is. It's basically a program in execution. And this program will typically execute in a sequential manner. So if you've ever written, have you guys written any programs? Are you doing any programming language course? Python, right? So every instruction you write, at the end of each statement is a semicolon. So when you finish writing that file and you compile it, what you create is a binary file, which is just a file with a list of instructions in computer code. So the computer fetches line by line each instruction and performs it. So each line, as the computer is performing it, it becomes a process. So the computer CPU fetches the instruction, decodes it, understands it, and then gets all the resources it needs, then it performs the action. But it can only perform the action for a limited amount of time. Because there are many programs running on your computer, the CPU time has to be shared. So in essence, what really happens is this. If I have multiple processes running on my computer, so let's say, for example, I have a process, let's call it P1, and another process P2, P3, P4, and P5. Basically, what is just happening is each of these processes has to have access to the CPU turn by turn. So it means P1 will go in first. After some time, if determined by the operating system, it will then be kicked out, whether it's finished or not. Then after that, P2 will then go. So P2 will then go. After P2 goes in for some time, it will then be forced to exit after its time expires, and then P3 can go, and then P4, and then P5. When they finish, they keep on shuffling. This is the concept we call multitasking. I repeat, this is the process we call multitasking. Now, in this example that I'm giving you, we have one CPU with one core. So all the processes have to share this one CPU. What if in the case where I have 2 cores or 4 cores or 8 cores? How does it work? In that case, I can have not only multitasking, but I can also have something called multiprocessing. Multitasking is just having many programs open and my CPU jumping from one program to another. Multiprocessing will only occur if I have at least 2 or more processing cores. So in this example now, I have 2 processing cores, which means if P1 is being seen by the first processor, let's call it CPU1 and CPU2, the second one can go and see the second processor. So if processor 1 finishes with P1, P3 can now go into processor 1, and P2, if it's finished, then P4 can go into processor 2, and they just keep on shuffling. 1 core per process or time. So the more cores you have, the more programs you can simultaneously run at the same time. Is that clear to everyone? People at home, can I get a thumbs up? A process is basically an instruction that runs on a computer. It runs on a CPU of a computer. And if I have multiple processes, then these processes have to share that CPU's time. The operating system decides how much time each process spends with the CPU. Can I get a thumbs up, everybody? Over on your reactions, if it's clear, just go ahead and give a thumbs up so that we know to proceed to the next item. All right. So let's carry on. So this is the definition of a process. Now, since there are many processes that can be running on a computer, each process has a unique identification number, like a name, but that name is unique. It has a process ID. So this process ID allows the CPU to know exactly who it's dealing with. And like we mentioned, it requires resources. So let me go ahead and show you on my computer. I'm going to launch something called the Activity Monitor. That's the equivalent of the Task Manager for Windows. So if you're on a Windows computer, you have the Task Manager. So over here, I'm going to zoom in a bit. You'll see I have multiple tabs that show my disk, my network, my energy, my memory, which is my RAM, and my CPU. I'm going to switch over to my CPU. So what you're going to notice in my CPU's view is here I have a list of applications, the names of the apps that are currently running. So these are the active processes on my computer, and you can see there are a lot of them. So let me look for Microsoft Teams. So here's Microsoft Teams over here. Here you can see how much CPU it's using. It's using about 50% of my CPU. Here is the amount of time that this application has spent open running on my CPU. You can see it here. About 27, I think this is 27 hours or something like that. Then this is the number of threads it has generated. I'll explain what threads mean later. Then all the way here, I have something called the PID. That is the process ID that I mentioned. That is the name of the process. It's a unique number so that the system, the operating system, can keep track of each individual process. So that's the identifying number. In the same way, what you're seeing here is a description of the execution of my computer. In a similar way, I can open AppSpace and take a look at my timetable, for example. So let me go to AppSpace, not Apple. On AppSpace, here's my timetable. So my timetable has some unique identifiers. For example, every venue has a unique identification number. Every lecturer has a unique name. Every group of students also has a unique group code. That is how we do the managing of processes and allocate resources as these resources are required. So this is what a process is. So when a process wants to execute, the resources it needs are allocated when a process is created or while it's in execution. So to illustrate this, I'm going to give you a real life example. Let's say after this class, this is your last class. Let's say you want to go see a movie. So that is going to be the process you want to engage in. You want to do a movie watching process. So there are a bunch of things that you need to watch a movie. One, you have to decide what movie you're going to watch. Two, you're going to have some money to pay for the tickets. Then you might need some money for the snacks and so on and so forth. You also need to determine what time that movie is on so that you can budget the money and the time to go see it. So if it's a movie that is 2 hours and to transport yourself there and back is another 1 hour, you need to budget 3 hours. So what we're saying now in a computer, this is what the operating system is doing. You double click on a program, the program is about to launch. That process for the program needs to then be created. At the time it's being created, the operating system will ask the program, hey, how much memory space do you need? That's like how much money. How much CPU time do you need? What are the input-output devices that you require? And are there any resources that you also require? So at the start of the process, all the requirements will be listed. Then the operating system will determine, do I have all these resources? If yes, we continue with the process. If no, we give an error message. Like you ask your friend, can we go see a movie? How much is it going to cost? It's 50 bucks. Okay, I have 50 bucks, no problem. What time is it? It's going to be from 9 to 12. 9 to 12 is too late. I can't go. I have something else planned. That means he or she doesn't have the resources to actually go watch the movie. So it's the same thing going on here. So all resources are allocated when the process is either created or in execution. But before running it, we have to make sure we have the resources. The operating system creates and deletes these processes. So anytime you double click on a program or you request for a function, the operating system will then allocate the necessary resources. Once it's done, it's finished, then we release those resources so that somebody else can use it. A process is also considered active while a program is passive. A program contains just instructions. A process is the CPU reading those instructions and performing the actions. An operating system keeps track of it using a process table. I just showed you my timetable. A process table and a timetable are very similar. It's a list of processes with certain characteristics and certain informations about those processes and the identification and so on and so forth. So this is what we saw when I opened my activity monitor over here. This is the process table. It contains all the processes running and the details that I need, or rather the details that my operating system needs in order to manage that process. Does that make sense? All right. So that's simple and straightforward enough. Let's proceed. So here's the first thing we want to learn today. Process states. So what is a state? A state can be defined as a condition, the condition or the context of a program. So if I ask you right now, what is your state? Some of you are sleepy. Some of you might be hungry. You might be happy. You might be sad. You might be tired. That's defining your current condition. So a state is your current condition. For a program or a process, what you have on screen are the states that the process can go through. And a human being throughout the day, you will change from one state to another. When you're tired, when you rest, you transition from tired to well rested. If you're hungry and you eat, you transition from hungry to satiated. When you're tired, you sleep, you're well rested. So you transition from state to state to state. So a process in execution also transitions from one state to another. So we want to try and understand what's going on here. When you double click on a program file and it starts to launch, that process is in a new state. In that new state, the operating system needs to determine what resources this particular process needs. And if those resources are available, then they can be allocated. What is the meaning of allocate? If I have $100 in my wallet right now, and I want to watch a movie, and I estimate the cost of transportation, the cost of movie tickets, and the cost of maybe snacks, let's say I estimate it to be $60, and I want to spend that $60 on that movie project, I can then allocate $60 mentally. I'll just say I have $100. I'm not going to touch anything except maybe 40. I have to have $60 reserved for that movie adventure. So that is me allocating $60 of the 100. I'm not immediately removing it and spending it. I'm keeping it in reserve. So even if I need to spend something, I'll spend up to $40 only because I only have 100 and I need 60 for this project. So I allocate 60. So allocation here doesn't mean the CPU or the process has been given that resource. It has booked it in advance. So there's a promise that it will get that resource. So that's what happens in the new state. So once we establish that the process has all the necessary requirements, it then transitions from the new state to the ready state. That means the CPU, or rather the computer, knows exactly what I need and it's available. So they can service me. So now I'm in the ready state. In the ready state, the process is waiting for its turn with the CPU. So what happens is there's something called the schedule dispatcher. That is the process scheduler. It decides from a queue of the ready state who is going to see the processor next. So when you're selected to see the processor next, you enter into the running state. So now I'm going to pause here and I'm going to give you an analogy that is going to help you understand and remember this. I'll go back to this new state and I'm going to give you a banking example. Let's say a customer visits a bank and wants to perform a transaction. That customer is the process. The bank clerk is the CPU. So what happens when you go to a bank? Immediately you step into the bank, two things you'll notice. There's an entry door and a security guard standing at that door. The minute you try to get in, the security guard will say, pause. What do you want to do? You tell him what type of transaction. You might say, I want to withdraw, deposit, transfer, whatever. The guy will then guide you to a queue number. You pick up your queue number, then there's usually a space for sitting down, then you go sit down. Once you sit down, you are waiting for service. So the minute you step in, you're a new customer. The minute you tell him what you want to do and the resources for what you need to do are available, he gives you a queue number and he allows you to go sit down. So that is now you in the ready state. You're sitting down, waiting for your turn to be serviced. Does that make sense? Now, if you go to the bank about 20 minutes before it closes, there's something interesting the Malaysians do. They close their curtains halfway. When you see a shop with its curtain closed halfway, what does it mean? It means we're still open, but we don't have time for any new customers. We're just waiting for the ones inside to finish. We cannot allocate more time. So we don't have the resources to process your request right now. And the banks do the same thing. So when you go to the bank and you see the door is open, it means go on in. They're ready for you. There are resources in time available for you. But if you see it's half shut, you won't be allowed in. Only those inside will finish and come out. So now you're sitting in the ready queue, you're waiting. The queue number comes up, it's your turn. That means the scheduler has chosen you. Now, in choosing who goes next, there's an algorithm that the bank runs. It's typically a first come, first serve. So an operating system can also implement that scheduling algorithm. In other words, the scheduler needs to choose which of the programs that are open goes to see the processor next. So that scheduler can operate a first come, first serve. So now you call, you enter, so you're now running. So you're with the clerk. The clerk says, give me your ID, give me this, you explain what you want. So after, let's say you want to do a transaction, you've told her all the details you need. She needs to perform the transaction. She might then ask you, can I have your identification and your credit card number? So maybe you have your credit card, so you just whip it out and give her. But your ID card, maybe your passport, you say, oh, sorry, my passport, I left it in the car. So what happens now is your process cannot be complete because there is data that is required. This is not a resource. It's data that has to come from you as a program. So until that data is available, the process cannot continue. So in that case, you will go from this running to a block state. The block state occurs whenever there is details that you are missing. Wherever, if you need something to happen or some piece of information, you cannot continue processing, so you go into a block state. So when your process gets into a block state, you will now have to go out, get to your car, get your passport, and then come back in. But when you come back in, the clerk is not going to just sit down and wait for you to go to your car and come back. He or she is going to likely continue with the next customer. So that is why from the block state, you don't go back to the running state. From the block state, you transition to the ready state because you have to wait for whoever is there to finish and you be called again. So you're waiting for the scheduler to call you again. So when she finishes with the customer, she now calls you. You go back, here's my passport. She can start doing the transaction. Another thing that can happen is sometimes when they put in all the details and they hit send, it might take a minute or two for the transaction to complete. If it's taking too long, the clerk can tell you, please, sir, have a seat. I'll deal with other customers. Once your transaction is done, I'll let you know. So this is now what's happening on this top line. An interrupt or a timeout has occurred. A timeout is you spend so much time with the CPU that the time allocated to you has finished. So you have to go out and continue again. I'll give you an example. This class is 2 hours. If I'm delivering this lecture and at the end of the 2 hours I haven't completed, I can't just continue going because your timetable might have other things on. So I have to stop where I stop and I have to then continue where I stop next week. So that's the same thing that is happening here. When I'm running and I run out of time, I might then be forced to leave because my time is out so that I can come back another time and continue running. So you'll notice in the running state, one of three things can happen. I am operating and I spend too much time. I finish the time allocated to me, so I have to be interrupted to go out. So I have a timeout. Or in the middle of my processing, an emergency happens that forces everything to stop. So you're in the middle of the bank, you're performing a transaction, and maybe there's a power interruption or there's a network break outage. So no processing can happen. So what happens? You have to go back to the ready state because nothing can happen. In this class, if we're running the class and all of a sudden there's a fire in the building, it's an interruption. We have to stop the class. So an interrupt or a timeout can occur. That's one. or I need more information or I need another action to happen before I can complete this process, so I transition to a block state. Or I come in, finish what I'm doing, and I'm done, so I enter the terminated state. Any questions so far? So people at home, any questions? Can I get a quick thumbs up? Can I get a thumbs up to indicate that I can move on? So everybody here comfortable, right? So this is the first component of today's lecture. This state transition diagram, you need to understand it. What do you need to understand? You need to know the definition and what happens at each state. And you also need to know how you transition from one state to another. For example, you can't go from the new state to the terminated. You can't go from the ready to the terminated, and you can't go from the ready to the blocked. So there are arrows here that you have to understand the transitions of. So let's move on. Here in the slides, you have a description of each state. I've already explained this. The new state is when a process is created and its resources are located. The ready state is when the process is now ready to execute and it's waiting for its turn. The running state is the state where the process has now been invited into the CPU. It has been fetched. It's being decoded. It's being executed. And in that state, it can finish, which leads it to the terminate state, or it can request for more information or wait for an action to happen, in which case it moves to the block state, or it can run out of time, in which case it moves back, it enters a block state and moves back into the ready state. Sorry, it goes to the ready state. And you, of course, you have the terminated and the block state, as we've already mentioned. So all of this is just showing you the different transitions. So now you have a quick question here. Is each of these transitions possible? Can you go from the ready state to the running state? Yes or no? Can you go from the ready to the running? Yes. What governs your movement or your transition from ready to running? The scheduler has called you and it's your turn based on an algorithm. That algorithm can be first come, first serve. So the first guy goes, the next time we pick the second guy, the next time we pick the third guy. Can you go from ready to new state? No, because it's impossible. You're moving backward. You go from new to ready, not ready to new. Can you go from block to ready? Yes. The block state is when you're waiting for some event to occur or you're waiting for some data. You enter the block state. Once that data is available, you move back to the ready and wait to be called again, and then you can proceed. So simple enough. Now, second thing we're going to learn today. We've learned the first one, which is the state. First, we know what a process is. It's a program in execution. The first concept we learned is that processes have states. There are 5 states: new, ready, running, blocked, and terminated. We can define, we know how we transition. The second thing we're going to learn, process control block. What is a process control block? Imagine it like an ID card. So on an ID card, you have a bunch of information. So if you look at your school ID card, there's a picture of you, there's your name, your TP number, probably the program that you're running, and a few other things. Now, if you were to say, go to the university administration and you wanted some help with something, maybe you wanted to submit a report, you wanted to make payment of your school fees or whatever, the first thing they ask you is, what's your identity? So your identity is going to be tied to your TP number. The reason why that is, can you mute? The reason why that is your name is not a unique identifier. In this university, we have thousands of Muhammad. So it's not a unique name. No name is actually unique. So we have your TP number, which is absolutely unique. No 2 students have the same TP number. So the first thing they will ask you is your ID. If they don't have your TP number, then they can't process you. Your ID is tied to that processing. And in order to process you, they need to know what you want and who you are. So your ID card contains all the details they need. So the operating system also needs an ID card for each program that is running. So the process control block is literally the ID card of a process. On that ID card, all the information that we need as the processor to deal with this process is available. So what is a process control block? It's a file that contains data about a process. I repeat, what is a process control block? It is a file, just like your ID card is just a maybe plastic sheet of paper with a plastic sheet with some information. It's just a file with a bunch of information that is required for processing this particular application or this process, for dealing with this process. So this is the information, some of the information available on a process control block. One, pointer to parent process. I'm going to go through each of this one by one. It's important that you understand what each is. The pointer to the parent process means if this process was created by another process. In other words, who's your daddy? If you have a father, that is another process that created you, then you will have the name of the father on the process control block. Let me give you an example. Let's say I'm in my kitchen and I'm trying to bake a cake. So the process I'm engaged in is bake a cake. So the first instruction in bake a cake is get flour and sugar and butter. So let's say my flour, sugar, and butter is in my cabinet, but my cabinet is locked. So my instruction says get flour, sugar, and butter. So I go to my cabinet to get flour, sugar, and butter. Then I find out my cabinet is locked. So I cannot execute that instruction. So that instruction, get flour, sugar, and butter, will have to create a new process called get key, unlock cupboard. Then I can get flour, sugar, and butter. Does that make sense? So get key is a child process of get flour, sugar, and butter. Does that make sense? So a process can create another process. If you create another process, that's a child process. To the child process, its creator is the parent process. So if you are a child process, the pointer to the parent process, the name of the parent process will be here. If you have children, the pointer to the child processes is in the next row. Then process states. You remember the 5 states we mentioned? New, ready, running, blocked, or terminated? That information is stored there. What is the current state of this process? The program counter. Do you guys remember what the program counter is? When we looked at CPU and memory a few weeks ago, we talked about special purpose registers and we talked about the program counter. What does the program counter contain? It contains the address of the next instruction to be executed. So here's how it works. Let me go back to my OneNote. So here you can see I have this file and I'm just going to make a list 1, 2, 3, 4, 5, 6, and so on. The way processes work is that every line of code is loaded as a process. So we start with line 1. When we finish with line 1, the process then transitions to line 2, then line 3. So imagine it. I'm in my kitchen. I am baking a cake and I have 10 instructions that I have to go through. It is me who does instruction 1. When I finish, it is still me who does instruction 2. It is still me who does instruction 3. So I am a process, but to run my program, I have to transition from each line of code to the next. That's why we said a process is a program in execution and it goes sequential. Now, because that is the case, this program counter is the address of the next instruction in the program that the process is supposed to go through. So we have that information also stored here. In other words, in the file, there are a bunch of instructions. Program counter will tell us what is the next instruction this process needs to perform. Then you have the register save area. Which registers have been allocated to this process? Memory limits. What is the memory address that has been allocated to this process? In other words, where is it stored in RAM? Priority information. How important is this process? Because your operating system, sometimes an emergency might happen. So if an emergency happens, it needs to deal with the most important processes before the least important ones. So let's say you're in class and it's important to attend this lesson. But while you're in class, you feel the need to go to the bathroom. That is going to be a process that has higher priority than you sitting in the class. Otherwise, you do something foul in class. So you have to leave. So because you have to leave, you have to suspend one process so that you can perform another. So in order to know which process is more important, every process will typically have a priority number. that will tell us how important it is in case we need to make a decision. Next, accounting information. This is the information about what program owns this process and what user triggered this process. So if I go back to my activity monitor here, you will note that apart from the process ID that I have at the end of this column, I also have a user. My username is Rin. So everything you see here labeled Rin is a process that I, the user, created. That is a program that I am executing. Whereas root is the operating system's operations. So the operating system is also executing processing. So if there were multiple users on this computer, you will see different names. If there were multiple system administrators, you will also see different names. So who created that process is what we refer to as accounting information. Is that clear to everyone? So the accounting information here is who owns this process and who is in control, who created it, and so on. And then lastly, pointer to files and other input-output resources. So a list of all the resources that this process needs will also be in the ID card called the process control block. So what is the process control block? It's a file that contains information about a process that the operating system uses to manage all the processes that are open and running. Very simple. Process control block, process ID card. What does it contain? Information about the process and its requirements. Finish. That's the second thing down. Any questions so far, people at home? Can I get a quick thumbs up? People, use your reactions under here. Quick thumbs up if everything is making sense and I can proceed. All right. So we can carry on. So here you have text that just describes the different process states. Third thing we're going into now, process scheduling. Now, before we jump into process scheduling, let me just give you a quick reminder. Everything you're learning, mostly in all your modules, especially this one, is you're learning new words. If you stop and take a look at the dictionary definition of each of these words, it will make things easier for you. What is a schedule? A schedule is just a timetable. What is a timetable? A list of activities with a list of resources required for that activity. So if I take a look at my class timetable, for example, if I come here, what does my class timetable show? They are basically 3 columns, right? There's the date and time, name of the module, and the group I'm seeing and the venue. Finish. So this is a schedule. It gives you my entire week. I have classes on Mondays, Thursdays, and Fridays. So on Monday, this is what it looks like. On Thursday, there's something else. On Friday, there's something else. This is my schedule. So a schedule is essentially a list of processes and the time that they require for execution. So what you're seeing on screen now, my activity monitor, is just showing you a list of processes. So the schedule will be the list, including the dates and times of what is required. So it says here a process enters the system. As a process enters the system, they are put on a job queue. So what does this mean? If you look at my computer right now, I have multiple programs open, right? These multiple programs each have their own individual processes. Now, let me remind you of something. A program can have multiple processes. I don't want you to think one program, one process. No. One program can have many processes. Let me show you what I mean. Over here on my process schedule or my activity monitor, you will notice that if I come down here to Microsoft Teams, there are a bunch of Microsoft Teams processes. That is because Microsoft Teams as an application is doing many things. There's a process that is capturing my screen and broadcasting it online to your screen. There's a process that is capturing my audio from my microphone and broadcasting it. There's a process that is looking at the date. There's a process that is looking at the time and so many things. So it's a bunch of things going on under the Microsoft Teams umbrella. So each job is broken. It's one program, but it has multiple jobs running concurrently, as you can see here. This is similar to what you have in your web browser. Your web browser is one application, but you can have multiple tabs open. Each tab can be a process that all belong to that one web browser application. Does that make sense? So a program can have one or many processes running under it. It's not one-to-one. So keep that in mind. So let's carry on. So that's what it's saying here. As processes enter the system, that is, as they're created, they enter something called a queue. What queue? The ready queue we mentioned, that ready state, you remember? From new to ready, that ready is a queue. It's a lineup of processes that want service. So the operating system has to look at this queue and decide who goes next. So the process, when it's new, it enters into the ready queue. The process waits until it's selected for execution. That is from the scheduled dispatcher. I'm in the ready queue. I'm waiting for my turn to be called. When I am called, I am allocated the time, and then I go in, whatever I need to do, I do, and I finish. So here's the diagram for the process scheduling process. Now, this diagram shows you how a process transitions into the system, but it also shows you how multiple processes are dealt with. So let's walk through it. This is the beginning of the diagram on the left-hand side here at the top. So when I create a new process, it enters the ready queue. What's the ready queue? Is the lineup. We're waiting for our turn to be serviced. So we are the customers at the bank who have our queue number and we're sitting down. So what happens to us? Our queue number gets called, then we go see the CPU. When we see the CPU, we said one of three things can happen. Do you remember what can happen? One, I finish and I terminate. That's the stop line. My process is so short and simple, no need to waste time. I go in, finish. Or I have an input-output request. In other words, the cashier has called me. I go, I'm doing my transaction, and they say they need my ID card, and my ID card is in the car. So I need a request to happen. What is the request? I need my ID card. So I need to go to my car and get my ID card. But look at something interesting here. In this example, there's an input-output request. It means that the process in this case needs data, but that data is going to come from an input-output device. So let me give you a different example. You go to Facebook or Instagram or TikTok.com and you have to log in. So that process is the TikTok login process. When we begin, the CPU begins to operate that login process. To do login, what do you need? Username and password. To insert your username and password, what hardware do you need? Keyboard, mouse, and screen. How many keyboards does a typical computer have? One. How many mouse? One. So since you're not the only process in the system, you are again going to enter a queue to wait for your turn to get keyboard, to wait for your turn to get screen, to wait for your turn to get whatever resource you need. So that's this input-output queue. Because there's so many processes. But remember, the CPU is so ridiculously fast that when it's operating, everything seems to like it's happening at the same time. So we human beings, because of how fast the processor, we don't even notice it's happening. So a 1 second wait for us is like 1,000 years for the computer, literally. That's how fast it is. It can switch between different processes so that it seems everything is happening all at once. So once we finish on that queue, it's our turn. We then do our input-output. Once we're finished with the input-output, we go back to the ready queue because now we can continue with the process. Or we're inside and our time allocated expires. We're given a few microseconds or milliseconds. Time is up, we have to leave. And when we leave, what happens? We go back to the ready queue, just like that previous diagram showed. That previous diagram was showing us the state transition. This diagram is showing us the same process, but it's showing us the flow of operation. So I'm back, I get admitted into the CPU. Another thing can happen. I create a child. So the term here, fork, have you ever heard the term fork in the road? A fork, the eating utensil, it's basically a stick that has 4 branches. So a fork in computing language means a branch. If you have in your Python code an if statement, you have a double branch. If true, do A, else do B. So your program branches into 2. So we call that a fork. So when a process creates another process, it means it's branching out. So we call that a forking of a child. So I know it sounds bad, but it's FORK, right? So the child process executes. So now if you are a parent process, you cannot complete your execution till the child process finishes. In other words, if the process is get flour and sugar and butter from the cabinet, and the cabinet is locked, I have to finish get key before I can do get flour, sugar, and butter from the cabinet. So that's what we mean here. So this child process will also enter this ready queue and go through this entire process that we mentioned. Does that make sense? The child process is also a process that needs to go through all of this. Or I'm in the CPU and an interrupt occurs. What's an interrupt? Some emergency situation, another program that is more important than me comes in. So the CPU has to deal with it. So let's say we're doing this class and the CEO of this organization comes in and says, we're sorry, students, but this venue, we need to do some servicing. Maybe this air conditioning is rickety and it's releasing maybe some toxic gas. So please excuse us. We have to cancel this class and we wish it. So that is an interrupt. So something more important than what we're doing has occurred. So when an interrupt occurs, we have to suspend the process that is currently running. And once it's suspended, the interrupt is now a new process that needs to execute. Once the interrupt executes and finishes, then the previous running program can return and then continue. Is this clear to everybody? So this is the second item. So people at home, can I get a quick thumbs up? Quick thumbs up if everything is clear, please. Use your reaction menu, not your raise hand, your reaction menu. All right. So let's carry on. So just to consolidate, we talked about concurrent processes a few weeks ago. We're going to revisit it. The word concurrent means multiple things happening at the same time. One of the benefits of modern day computers is they can multitask and they can multiprocess. Multitasking is a situation where you have multiple programs open, like I have here. I'm multitasking right now because I have multiple programs open. Multiprocessing is different from multitasking. Multiprocessing, my system needs to have at least 2 or more CPUs. So you have 2 or more processes running at exactly the same time. And that can only happen if I have 2 or more cores. So I can be multitasking and multiprocessing. Because remember, a single program can have multiple processes. So we're just looking at the processes. So I can multiprocess and multitask at the same time if I have 2 or more processing cores. With one processor, I can only multitask. With 2 processors, I can multitask and multiprocess. So the term concurrent processes means basically multiprocessing. So when I'm multiprocessing, there are processes that are independent and there are processes that are cooperating. What does this mean? It means sometimes in our system, 2 or more processes can have a relationship and a dependency on each other. One depends on the other in order to operate. And in some cases, they're all independent. They can run independently of each other. I'll give you an example. Let us say this classroom, we wanted to clean it. And the process for cleaning it is we need to wipe the windows and the furniture. We need to vacuum. So we need to vacuum and dust and wipe the dust off the furniture. So our process is as follows. Number one, we have to remove the furniture so that we can vacuum effectively. So the removing furniture process has to happen before the vacuum process. So there's a dependency there. One has to execute before the other. So you can have in a typical process between processes that kind of dependency. One has to execute before the other. Or in some cases, one is passing data to the other. So let me give you an example that will introduce us to threading. So I'm going to go over to YouTube and I'm going to look up Super Mario Brothers 1, which is an 8-bit computer game. And I'm going to use this and as an example to actually run. Now, we know that when this game is being played, there are a bunch of things happening. We have a soundtrack, and we also have sound effects. What's the difference between soundtrack and sound effect? Soundtrack is the background music that is playing. You can hear it if I unmute. The sound effect is the sound that made when there's an action performed. When Mario jumps, there's a sound. When he picks up a coin, there's a sound. When he shoots a fireball, there's a sound. When he interacts with an enemy, there's a sound. So that's the sound effect. In the system here also, there's a score counter, a coin counter, a world counter, and a time counter. All of these things are individual processes that are part of the program Super Mario Brothers 1. So this program has a process for managing score. There's another process for managing score coin count, another process for managing world count, another process for managing time, another process for managing Mario's individual animation, another program for managing Mario's interaction with the environment, another process scrolling the background, another process, the enemy AI, and so on and so forth. So in this example, which of these processes are cooperating and which of them are independent? Is the score counter process an independent or a cooperating process? Is the score counter an independent or a cooperating process? In other words, does it need another process in order to function? Huh? You think it's independent? How is the score generated? Hold on. It's based on Mario's interaction. So if Mario takes a coin, score counter increases. So Mario's animation and position in the game is a process that helps the score counter determine if I am going to increase score. Because as you saw just now, when you shoot an enemy, you get 200 points, and you can see the 200 display on screen. I'll repeat that. When he shoots the enemy, 200 appears on screen. That animation of the fireball interacting with the enemy is a separate process from the score counter. So these two are going to be cooperating processes. Does that make sense? Now, as Mario is moving, you will notice that the screen background is also moving. So the background screen movement, is it a cooperating process or an independent process? It's cooperating with another process, Mario's position on the screen. What about the time counter? Is it an independent process or a cooperating process? What is it cooperating with? Huh? What is it cooperating with? It's not, it's independent. The timer just runs. Right now, if we had a clock in this class, the timer just runs. It doesn't give a damn what we're doing. Let's say we decide to pause for a 5-minute break. The timer is just still going to keep on running. So in this particular implementation, there is no relationship. We can build it so that there's a relationship. So like when I'm playing the game, in reality, if I hit the pause button, the timer also stops. So in that case, we say it's cooperating. But assuming we don't have that stop function, it becomes an independent process. You get it? So it's easy to distinguish if you understand the operation of the program. So that's that about cooperating concurrent processes. So some are dependent, some are independent. So you can have independent or cooperating processes, basically. Why would an operating system permit cooperation between multiple processes? The reason why we have that is because it makes processing more efficient. If you have processes actually cooperating, you can actually save resources. So imagine if this Mario Brothers game has multiple processes running. If these processes are cooperating, they can share memory and they can share the CPU time. It makes them a little bit more efficient. So it reduces the requirements that they have. So we now enter the concept of threats. A thread is defined as a lightweight process. A process is defined as a program in execution. Is there a difference between a process and a thread? Yes, we said a thread is still a process, but it's a lightweight process. So what do we mean by a lightweight process? We go back to the Mario example. In the Mario example, if we compartmentalize each operation, we can create that operation as a simple function. So for example, the timer is a simple function. So it can run as a thread. It's a process, but it's very lightweight. It's only doing one thing. Count time, finish. Then you have another process, count coin. It's a thread. You have another process, world counter. All it does is counting the world level. It's a thread. So a thread is a lightweight process. As computer programmers, later in your level 2, you are going to do a programming module called concurrent programming. There's a module called concurrent programming. What that module teaches you is you've already learned, let's say, how to program in Python, right? You will learn how to program threads in Python. In other words, the way you write your code, you're going to now write it. You're going to simplify each line of code so that they can run concurrently. In other words, it's a style, it's a methodology of doing something. Let me give you a simple example. When you wake up in the morning, in your head, you can make a list of all the things that you need to do in sequence. I'll do this, then this, then this, then this, then this. You can make a complete list. Now, the way you make your list will affect your productivity that day. Take, for example, let's say you decide you want to have breakfast, but your class starts at 8:30. And you want to eat at, let's say, 11. So option 1 is you can say, all right, I'll go to school, do my first class. When I'm done at 10:30, I come back home, do my breakfast, then come back for my afternoon class. Another guy will say, that's a little bit of waste of time, energy, and maybe money if they're driving because they have to consume food. So he says, I wake up in the morning, I make my breakfast, take my breakfast along with me to school, do my class, then eat my breakfast in school, and then continue. So which one is more efficient? The second one. So in the same way as a programmer, when you're writing those instructions, you can write it in such a way that you can have several parts of your program running at the same time because they are not dependent. It's not a sequential program. Step 1, step 2, step 3, step 4. The steps are now independent. Some are dependent, some are independent, so you can run both at the same time. I'll give you a very good example. The example here for if you have a situation where we want to clean this classroom and we've decided the first step is to remove the furniture, vacuum, dust, then rearrange the furniture. So we have 4 steps. If one person is going to do it, it's very simple. Remove furniture, vacuum, dust, rearrange furniture. What if you have 2 people doing it? In this situation, they will have to work together to remove the furniture, do the vacuuming, but to do the vacuuming, you need 2 vacuum cleaners. Let's say you only have 1 vacuum cleaner. Is it possible for person 2 to be doing something concurrently while person 1 is doing something else? If yes, then you've written a concurrent program. So you write concurrent programs by making your programs into your program instructions into threads. So a thread is a lightweight program that can execute. So what is the process control block? Do you remember? What is the process control block, people? Huh? It's a file that contains details about a process that help the operating system manage that process. Can you draw and explain the scheduling diagram? The scheduling diagram is this guy. Observe it and understand it. From the ready queue, a process is then selected based on the scheduling algorithm to go to the CPU. One of several things can happen. The process gets terminated when it finishes, or it has an input request where it enters another queue for input output. Then it does its input output when it's its turn with the input output device, and then it goes back to the ready queue for further processing. Or the time can expire in which it's forced out into the ready queue to wait for its turn again. Or it can create a child process, in which case it now has to wait for this child process to go through all of this and finish before the parent can come and continue. Or an emergency interrupt occurs, in which case we have to wait for that interrupt to finish before the process can resume. So that is the process scheduling diagram. So I hope that is clear to everybody. So a thread is a lightweight process that can execute independently of other parts of the processes. In other words, it can run concurrently. Multiple threads can run concurrently. It can be present for user processes, that is applications that you install, or system processes, that is the operating system itself. So the creation of a new child process from an older one is called spawning or forking. So we're done with that first part. This is an activity. I've uploaded the slides. You can come back to this activity later. Now we want to enter into the next section of our discussion, which is the actual scheduling. We've mentioned scheduling as an activity that decides which of these processes goes next. An example of a scheduling system is first come, first serve, right? So we are now going to look at CPU scheduling properly now. So the scheduler is a program in the operating system whose job is to select which process goes next in the ready queue. You remember the ready queue? That's this guy here. The scheduler's job is to decide who goes next. That's all. And in order to determine who goes next, it has certain principles that it follows. It uses something called a scheduling algorithm. Now, people, do you know what an algorithm is? This also extends to the people at home. What is an algorithm? Huh? A method of solving a problem. An algorithm is a method of solving a problem. There's a very distinct distinction between an algorithm and a process. A process lists out exactly what you need to do. An algorithm tells you what you need to do to solve a problem. For example, if I bring a child over, a young kid of maybe, let's say 4 or 5 years old, and I teach the child 2 plus 2 is 4. The child can memorize 2 plus 2 is 4. But that doesn't mean the child understands addition. Because if I said to that same child, all right, I teach you 2 plus 2 is 4. What about 3 plus 3? They will have no clue. Until I teach them mathematics, addition particularly, then if I teach them addition, I can give them any 2 random numbers and they can work it out. So the knowledge of addition is an algorithm. It's a method of solving a problem. In this case, it's an additional problem. Does that make sense to everybody? So an algorithm is a method that once you're taught, you can solve problems of that nature without being given, without needing to be taught the specifics. You're just taught the concept, division, addition, multiplications. Once I teach you that, I can give you any 2 numbers and you can perform that. That's the difference between an algorithm and a process. Your computer programs are processes. What you say is what happens. If the computer encounters something it doesn't understand, your program crashes. An algorithm, on the other hand, is a methodology of solving a problem. So there are some computer applications that actually use that. Like, for example, this AI, it uses algorithms basically to identify and distinguish and make decisions. It's not procedural code, it's algorithmic. So that is the algorithm. Scheduling is a fundamental function of an operating system. We mentioned it as one of the 3 core functions. We said that all operating systems, no matter how simple or complicated, accept commands from users, manage hardware, manage software. Those are the 3 operations. So in managing hardware and software, we're doing scheduling. So scheduling is part of that managing of hardware and software resources. So scheduling is done to ensure that the CPU is not idle. Now, this is a very important and interesting point. I want to define the term utility. In business, utility comes from the word utilize. To utilize something means to make full use of what you have. For example, you come to school 5 days a week. You have one car and you drive that car every day. You're fully utilizing the car. If you're very wealthy and you have 5 cars and you have your Monday car, your Tuesday car, your Wednesday car, we can make an argument that you're not utilizing the cars because most of the time the cars are just sitting down doing nothing. Does that make sense? So when you have a computer and there's work to be done, the scheduler's function is to ensure that if there's work to be done, your computer doesn't sit idle. It produces, it does work. We don't want it to sit down wasting time. We want it to do work. So when a scheduling algorithm is being designed, the goal is as follows. So now in part 2, this is the first thing we need to learn. What is the aim of a scheduling algorithm? So when computer scientists are defining a scheduling algorithm, what is the goal? 1, fairness. What is fairness? We want every process to get its fair share of CPU time. What does fair mean? Some people confuse the word fair with equal. They're not the same. Let me quickly illustrate on one note. If you have, let's say, the value 5, 5 is equal to 3 plus 2. So 5 is equal to 3 plus 2. No problem there. Equality is a mathematical concept. But equal is not the same as fair. So what is the definition of fair? I'll give you a quick example. Let's say there are 3 kids. One, the youngest, maybe 5 years old, tiny little fellow. The next guy, the medium child, maybe he's about 10. And then you have the oldest, which is taller than all of them, bigger, taller, and stronger. So let's say these kids, they want to watch a football game from behind a fence. So let's say the fence is this high. The fence is this high. So you are their parent. You want to give them a box to sit down or to stand up on so that they can watch the game. Problem is, if you give each of them a box, the oldest guy doesn't need the box. He can still see the game. But the youngest guy, even though he has one box, still cannot see the game. So is this situation fair? 2 can see the game, 1 cannot. It's not fair. But is it equal? Yes, everybody has one box. So this is the difference between equality and fairness. So what needs to happen now is the older kid needs to give the younger kid his box. And if they give him that box, then the younger kid can now enjoy the game as well. But he has 2 boxes. So this is fair, but it's not equal. So this is the same concept here. Fairness means that each process is given what it needs to complete its work. So some processes will get more resources than others. But the goal is everybody should get what they need. Efficiency. The CPU utilization should be kept at maximum. We don't want any wasted time. So if we have an algorithm, the algorithm should concentrate more time on doing work than doing anything else. Third, response time. We want a situation where if a process is running, it should be able to generate a result as quickly as possible. I'll give you an example in a restaurant. If I go to a restaurant and there are 10 other customers that arrive with me, who should the customer treat first? What would be fair? First come, first serve. So if the restaurant is deciding on an algorithm on how to deal with its customers, it will operate first come, first serve. If it's concentrated on efficiency, let's say of the 10 of us, 3 people have ordered fried rice and chicken. The restaurant chef can make fried rice and chicken 3 times individually or combine all 3 together in one and improve efficiency. So you do the 3 at the time it takes to do one. That's efficiency. Response time. In the restaurant, when you go and you make an order, depending on what you order, it can be short, it can be long. But if it takes a long time, and the restaurant doesn't give you any feedback, you will feel a little stressed out. This is why when you go to a restaurant and you order food, they will typically bring the drink before they bring you the food. The reason is they want you to relax and know that they are working on your procedure. So it helps you relax. If they don't bring that drink, you'll feel agitated because you're not sure what's going on in the kitchen. So that's why they do that. So that is the same thing in computer programming. The response time is the time it takes for your program, when it's executing, to start generating results. It's not completed processing, but it's generating results. Take, for example, you're copying a large file, maybe a 5 gig file from a pen drive to your hard drive. You'll see the progress monitor. It's showing you it's building. That's a response. Imagine, do you know that thing is actually an invention? Once upon a time, computers didn't have that. If you copy paste, you just have to wait and trust. You don't really know what's going on till it finishes. You don't know if it's stuck. You don't know if it's going fast. You don't know if it's going slow. So the response time is the animation that sometimes plays when you interact with a program. So it can be a progress bar. It can even be an animation. You double click something, you see that zoom in animation. It tells you something is happening. That's response time. You want to keep the response time consistent and short. So if I go to a restaurant and I place an order and within the first 3 minutes, they already bring me the drink, that's good response time. It might take them another 10 minutes to bring the actual food, no problem. But that's the response time, the amount of time it takes for the first results to start being generated by the process. So an algorithm that has a short response time is a better algorithm than one that has a long process time. Then you have what we call turnaround time. Turnaround time is defined as the complete time it takes to start and finish the process. So if it's in the restaurant example, that's the amount of time it takes them to complete your order. So maybe if you order fried rice, chicken, maybe it took them 15 minutes. So 15 minutes is the turnaround time. You want a short turnaround time for your algorithm to be good. So minimize that time and keep it consistent. Lastly, the throughput. The throughput is now defined as the number of processes completed per unit time. So for example, if I have several algorithms and I want to compare them, I can say in 1 hour, how many processes did this algorithm finish versus this guy? If I wanted to compare restaurants, I can say in 1 hour, how many customers did this guy finish dealing with versus this guy? Per unit time. I can say per hour, per minute, I can say per day. So throughput is number of jobs per unit time. Number of jobs per unit time. And we'll see how that is expressed later on. Now, in terms of these scheduling algorithms, there are 2 types. There's the preemptive and there's the non-preemptive. What's the difference between the two? The term preempt is an English word that means to take a decisive action before the fact. For example, you're sitting down and from a distance, you see somebody coming towards you and the person looks dodgy, looks like a criminal, and you're worried that they might actually attack you. And you see them reach behind them, they're getting closer and they start removing maybe a knife or a machete. You're not going to wait for them to swing. You might preemptively start running if you're smart. You understand what I mean? Or if you can fight, you might attack them before they attack you. So to do something before you are prompted to do it is what we call preemption. In the case of an operating system and process scheduling that we're talking about, the term to preempt literally means to be interruptible. Let me explain. This is a little bit of a difficult concept to understand. If I open up my timetable here, Is this timetable preemptible? Meaning, can I alter this timetable? No, it's fixed. Date, time, group is fixed. A preemptible timetable will be a timetable that I can adjust manually. In other words, I can move things around and I can change things. No problem. So computers can be created to have a preemptive operation or a non-preemptive operation. What's the difference between the two? Right now, my computer is running my browser. So on screen, you see my browser. I can jump from my browser to my Teams application. I can jump from my Teams application to my OneNote application. So whatever timetable or schedule for processes that have been arranged, by me switching attention from one program to another, my timetable in the background is actually changing. The CPU and the operating system is saying, hey, the guy wants this program now, so all our resources will be dedicated to this program. If I switch to another program, all the resources are now dedicated to this. So my operating system is a preemptive algorithm. It's running a preemptive algorithm. That is why I can jump from one program to another. If it was a non-preemptive, a program must start and finish before I can do the next program. I won't be able to multitask. I won't be able to multiprocess. I won't be able to jump around. Does that make sense? So to preempt means you have the freedom of altering the schedule. Non-preemptive, you can't alter the schedule. So like now you can imagine in this class, there are some people right now online, they're saying, hey, can we have a break? Can we have a break? So a break would be to preempt the class. Stop it for a while, go do something, come back, and then continue. So that would be to preempt. But in today's class, we're not going to preempt. So sorry, we need to finish. We have a lot to go through, so I'm worried. I'd rather finish early than interject in the middle. So please be patient. Now, continuing along with this preemptive versus non-preemptive, you will see it demonstrated in a bit. So for the preemptive algorithms, you have round robin. These are the names of the algorithms, and we're going to look at them in a minute. And there's multi-level feedback queue and multi-level queue. Then for the non-preemptive, you have first come, first serve, shortest job first, and priority. So let's take a quick look. Why is CPU scheduling important? So people at home, you can participate also. Why is CPU scheduling important? In a single sentence. Why is scheduling important? Scheduling is planning. Why is planning important? One sentence. So process first, then speak later. Not false, but that's not the best answer. You can do better than that. He says to get the task to run smoothly. Yeah, but that's not the primary objective. What? It helps to do what? So process first, then speak. So another guy online is saying to make sure everything runs smoothly. That's not the best answer. It's a correct answer, but that's not the best answer. Keep track. That's what everybody's saying, but that's not the best answer. There's a better answer than that. To avoid conflicts, you mean? It has that goal, but that's not the primary goal. So some guy here online is saying, Yichi is saying to run more jobs, as many jobs as possible. Another guy follows up Yisheng is saying efficiency. That's closer to the answer. The word we really want, efficiency is a good word, but a better word is maximize utility. That's the goal of the algorithm, to maximize utility. That is to make the best possible use of what you have, the resources you have, to deliver a service. So that is the main goal. What is the difference between a preemptive and a non-preemptive algorithm? It's very simple. A preemptive algorithm can be interrupted. That is, the plan can be interrupted. A non-preemptive algorithm, the plan cannot be interrupted. Give two examples of each. We've already looked at them here. For preemptive, round robin, multi-level queue, multi-level feedback queue. 3 examples. For non-preemptive, first come first serve, shortest job first, and priority. Now, we want to take a look at those algorithms. When we're looking at these algorithms, remember, computer scientists are the ones that sit down and design these algorithms. When designing the algorithms, we have to test them. To test them, we have to perform calculations. And those calculations have these keywords. CPU utilization. I can show you that calculation happening on my activity monitor. If I zoom in and I go down here, you can see from my CPU, my system, my operating system is using between 3 to 7% of my CPU. My applications are using about 12. And idle, about 80% of the CPU time is idle. Does this mean my computer is not efficient? No, it's efficient. I'm just not doing many things. I don't have many processes or tasks. So you can see my efficiency is actually being calculated. So this is the value for my CPU utilization, is the percentage. How much of it I'm actually utilizing now. And I'm not particularly utilizing the CPU right now because I don't have many tasks running. Next, throughput. Throughput is the amount of time that if you look at the aims here, we have throughput as the number of jobs completed per unit time. So how many jobs can we finish using this algorithm in a particular unit of time? Turnaround time is the amount of time from the start to finish of one job. Throughput is the number of jobs we finish in a particular given time. Turnaround is the time for one job's completion. Waiting time, how much time does a process spend waiting in that algorithm? Let me give you an example now. If you have 10 customers arriving at a restaurant and we're going to operate first come, first serve, it means when the first guy is placing his order, number 2 to number 10, what are they doing? Waiting. Then when we get to number 2, number 3 to number 10 are still waiting. When we get to number 3, number 4 to number 10 are still waiting. So if we implement a first come, first serve algorithm in a restaurant, we can calculate on average how much time each person has spent waiting by calculating individually how much time has each person waited and then averaging. We can also calculate how long it took every person's job to finish by simply calculating how long they were in the restaurant till when they got their order. And that's what we're going to do now. So that is the turnaround time and the waiting time. The response time is the amount of time between when the job was submitted and when we started getting results. You'll see that in real time. And the burst time is the amount of time each job requires. So in order to demonstrate the round robin, here's what we're going to do. This is the characteristic of the round robin, which is a preemptive algorithm and is the first of which we're going to look at. It's the oldest, simplest, and fairest and most widely used algorithm. It is designed for multitasking systems. Multitasking also is called time sharing. The time slice or time quantum is defined for each of the processes, and the ready queue is treated as a circular queue. So here's what it looks like. When computer scientists are going to perform a test on any algorithm, this is what they have. I'm going to just delete a couple of these. This is essentially the problem. So one, you have a table with a list of processes, P1, P2, P3, P4, and P5. The 1, 2, 3, 4, 5 is a label that determines when they arrive. So P1 means first to arrive, P2 second to arrive, P3 third to arrive, and so on. The burst time is the amount of time each process needs with the CPU. So P1 needs 10 milliseconds, P2 needs 1 millisecond, P3 needs 2, and so on. So far, so good? Now, in this round robin technique, it is a preemptive algorithm. So because it's a preemptive algorithm, it has a 2 millisecond time slice. What does this mean? It means that every 2 milliseconds, the processor is going to pause and take a look around to see if there are any important processes to run, and then carry on. Now I'm going to pause here, and I'm going to explain a very important concept. How does a human being interact with the real world? So people at home also participate. How does a human being interact with the real world? Very good. So somebody online says through the 5 senses. If you can't see it, you can't hear it, you can't taste it, you can't smell it, and you can't touch it, as far as you're concerned, it doesn't exist. So because human beings, we can respond to these 5 senses, we call it response to stimuli. So if I'm sitting down in this class and I'm delivering this lecture, somebody can come and give me a pat. That pat will send a signal to my brain to say, somebody needs your attention. And I can then stop what I'm doing and then pay attention to the person. My phone in my pocket can begin to ring. It can interrupt me. If it starts to vibrate, I'm aware of it. I take it out and I stop what I'm doing to interact with it. Now, I want you to imagine if you wanted to get the attention of my computer now. Since it doesn't have the sense of touch, I can't do this unless it's a touch screen. Then I have to touch the screen. So the concept of preemption has to do with getting the attention of the CPU, getting the attention of the computer. So right now on my screen, you see my Teams application is running. If I want to switch to another application, I touch my mouse. The minute I interact with my mouse, the computer registers that interaction, and then it interrupts what the PC is currently doing. It's only able to do this because I am running an operating system that is a preemptive operating system. In other words, if my system wasn't preemptive, I can't do it. It will only be able to run one program at a time. It will run the program from start to finish, then change. Do the second one, then change. Do the third one, then change. Does that make sense? Let me give you a good example. I'm sure everybody here has a washing machine of some type. So if you have a washing machine, depending on how sophisticated your washing machine is, you have many types. Now, do you guys remember this washing machine? This is the broke guy solution. It's the cheapest washing machine you can get, and it's hella manual. So it has 2 compartments. So you put your clothes in a wash sack, you put it in the wash area. After it finishes washing, you have to then take it out and put it in the spin dry area. Then it spins. So everything here is manual. You can't preempt this process. Once it starts, you have to go through that process from wash, then to rinse. You now fast forward to this top loader. So your typical top loader, when you put in your clothes and you select the wash, what does it do? It soaks, then it washes, then it rinses, then it spins. That's the processes it goes through. Can you change those processes once they've started? No, because this washing machine runs a non-preemptive algorithm. Once you press that start button, that's it, game over. It's like you when you enter an aeroplane. The minute they lock that door, you're in the pilot's good care. There's no in, no out. You're done. You don't have any, your life is out of your hand. The minute that door closes, your life transfers to the pilot, basically. So a non-preemptive algorithm application is one in which when you start a process, it doesn't stop, it doesn't end, it has to transition naturally. I can't in the middle of the wash cycle tell the washing machine, hey, you were doing wash for 20 minutes, I want you to add another 20 minutes. You can't do that. You can terminate and restart, or you can wait to finish and restart, but you cannot change the flow. Does that make sense? So there's some computer applications that are also built like that. Once you start the process, it doesn't stop. And then you have the intelligent washing machines, the smart ones, the sophisticated ones. They're more expensive. So these guys, they can even tell you what time of day it is. You put something in, you can communicate with them via your phone. You can tell them to start, pause, stop, change, whatever, no problem. They're more sophisticated. So this is the implementation of the preemptive versus the non-preemptive. So for a computer to be preemptive, it needs to implement this logic. So here, what we're seeing is a demonstration. Let me show you what it means. If I am going to, let me do it this way. I'm going to copy this image and I'll put it on OneNote so that we can solve it together. So here is the information I have. I have 5 processes. I've been asked to run round robin. How do I do it? The round robin system operates on a graph to do the calculation. So my graph is a one-dimensional graph. It begins with 0, straight line here. So I can partition it into groups of 2. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So here's how the round robin works in real life. Since P1 is the first process to arrive, we load P1 in the first lock. So we're going to put a box around P1. And note that P1 needs 10 milliseconds with the CPU. But the time slice defined is 2 milliseconds. This time slice is the system telling the CPU, the maximum amount of time anybody can spend with you is 2 milliseconds. Anything more than 2 milliseconds, kick them out, let them go out and come back in. Just in the same way, this class has a 2-hour time slice. If we've not finished covering a topic in this 2 hours, we have to suspend it till the next class next week. That's the same thing with this algorithm. You have to suspend it and do the next processing till you finish, then you come back to those that haven't finished. But the maximum time each one will spend is defined by the time slice. In this example, 2 milliseconds. So that means even though P1 needs 10 milliseconds, at the 2 millisecond mark, we have to stop, which means P1 needs 8 milliseconds more to complete processing. So far, so good? Right. So the round robin, when it finishes with P1, although P1 hasn't finished, it transitions to the next guy, P2. P2 only needs 1 millisecond, but the maximum is 2. Since 1 is less than 2, no problem. That means P2 can go in at the 2 millisecond mark and finish by the 3 millisecond mark. So I'll put an asterisk here to say that it's finished. So P2 is finished, no problem. Entered, process, terminate. Then it transitions to P3. P3 has 2 milliseconds, which means it can also complete. So from the 3 millisecond mark, it enters, and at the 5 millisecond mark, P3 is complete. We put an asterisk to say it's finished. No problem. Then we transition to P4. P4 also only needs 1 millisecond. So it means from 5, we stop at 6. So this is P4. P4 also finished, terminated. Then we go to P5. P5 needs 5 milliseconds. So from the 6 millisecond mark, since 5 is greater than 2, the maximum we can spend is 2. So from 6, we have to stop at 8. So this is P5. And P5 still needs 3 more milliseconds to go. We've reached the end of the list. So what happens? The round robin now cycles back. It starts back at P1. So it now looks at P1. P1 now needs 8 milliseconds, but maximum is 2. So we go in for 2. We stop at 10. So this is P1. We still have 6 left. Then we go to the next guy. Remember, P2, P3, and P4 have all finished. They're terminated and gone. So we go for P5. P5 needs 3 milliseconds more. Maximum it can do is 2 milliseconds. So we do the 2 milliseconds. So this is P5. P5 now has 1 millisecond left. So we've reached the end of the list again. What happens? Go back to the beginning. So we're now here again, P1. P1 has 6 milliseconds left. We can only do 2 milliseconds. So this is P1. We still have 4 milliseconds left. P5 has 1 millisecond left, so it goes from 14 to 15. So this is P5. So P5 is now finally finished. So now the only guy left is P1. P1 has 4 milliseconds. We cannot stay 4 milliseconds, so we can stay a maximum of 2, which means at 17, even though we don't have any other process, we still have to stop P1. And we have 2 milliseconds left. Then readmit him again, and at 19, P1 has finally finished. Now, I want to explain that every time we stop and change process, there is wasted time. If this was a restaurant, what it means is the order for customer 1 needs 10 minutes, but the chef can only work on any one item for 2 minutes. So it means I start working on this guy's fried rice. After 2 minutes, I stop everything and I take it off the fire and I keep. That stopping and taking it off the fire consumes time. Then picking up customer number 2's order and loading it also takes time. Then I start processing it. After another 2 minutes, I have to stop customer 2 and keep. Then go to customer 3. So, but if I finish customer 2, finish. Then 3, you get the idea. So that start, stop causes extra wasted time. But the beauty about this algorithm is if you observe, it's kind of fair. Everybody is getting 2, 2, 2, 2. So in other words, if you're customer number 2 and customer number 1's order is 10 minutes, it literally means you have to wait 10 minutes before they even start dealing with you, which is not fun. But if everybody is given 2 minutes and your order is a very short order, no problem. Within 5 minutes, you're done. But customer 1, because his order is long, he has to wait longer. And he will be the last to be served in this case. So if a restaurant did a round robin technique, it means first come, last serve in this example. Is that a bad thing? Not necessarily. Like we said, by the time the last customer gets it, the other 4 customers have already been serviced and they've probably gone on with the rest of their lives. So is it really bad? From an efficiency point of view, maybe not so much. So what the computer scientist needs to do now is to determine how efficient this algorithm is. To do that, we need to calculate on average, how long did each customer spend waiting? On average, how long did it take each customer from start to finish? So we will do that. So now we want to calculate something called the average waiting time for each process. So the average wait will be given for P1, P2, P3, P4, and P5. So we have to calculate this individually. So how long did P1 spend waiting? We will see here that P1 was the first. So it starts by not waiting. He was the first customer. He went in and operated for 2 milliseconds. But from this 2 millisecond mark, P2 took over, then P3, then P4, then P5. So from 2 to 8, P1 was waiting. So 2 to 8 is how many milliseconds? 6. So we say 0 plus 6. Then at the 8 millisecond mark, P1 continued till 10. But from 10, he got kicked out and he waited all the way till 12. So 10 to 12 is another 2 milliseconds, so plus 2. Then he operated from 12 to 14 and then stopped from 14 to 15, so plus 1. And then for the rest, he just operated in and out, in and out. So in total, P1 spent 9 milliseconds waiting. What about P2? P2 at 0 was waiting for P1 to finish. Then after 2 milliseconds, it entered, then finished. So P2 only spent 2 milliseconds. What about P3? P3 was waiting from 0 all the way to 3 milliseconds, went in, then finished. So P3 waited only 3 milliseconds. What about P4? P4 was waiting from this 0 all the way here to 5 milliseconds. So P4 waited 5 milliseconds and finished. What about P5? P5 is waiting for P2 from 0 all the way to 6, then waited from 8 to 10, then waited from 12 to 14, and then finished. So here P5 at first waited 6 milliseconds, then 2, then 2. So 6 plus 2 plus 2 gives us 10. So on average, these processes waited 9 for P1 plus 2 for P2 plus 3 for P3 plus 5 for P4 plus 10 for P5 divided by the number of numbers, which is 5. So on my computer, if I say 9 plus 2 plus 3 plus 5 plus 10, is it plus 10? Yes. Divided, all of this divided by 5, I get 5.8 milliseconds. So my average wait time is 5.8 milliseconds. So if this was a restaurant and I asked the question, on average, how long do you have to wait in this restaurant to be serviced? 5.8. You get it? Then we will also calculate the average turnaround time. The average turnaround time is the average time it took for everybody to finish. So average turnaround time. Again, we will have to do for P1, P2, P3, P4, and P5 individually, and then aggregate and find the mean. So P1, when did it finish? All we need to do is look at our Gantt chart. By the way, this thing is called a Gantt chart. So all we need to do is look, when did P1 finish? P1 finished here at the 19 millisecond mark. So this is 19 milliseconds. So P1 finished at 19 milliseconds. It means it took it 19 milliseconds from start to finish. What about P2? P2 is right here. So P2 finished at 3 milliseconds. What about P3? P3 finished at 5 milliseconds. What about P4? P4 finished at 6 milliseconds. What about P5? P5 finished at 15 milliseconds. So now we calculate the average again. So we say 19 plus 3 plus 5 plus 6 plus 15. So once we have all that, we can then divide it by 5, which then gives us 9.6 milliseconds. So what this means is, on average, how long does it take you to go to this restaurant, eat and finish, or be serviced? On average, 9 milliseconds. Within 9 milliseconds, you're done. Your order will be complete. So now if you've created an algorithm and you've performed this test on it, you can then create other algorithms and then test these values. And that's what we have in the rest of the discussion here. So from the round robin algorithm, you will notice its characteristic. It's every 2 milliseconds, it stops. In this example, remember this time slice can be 3 milliseconds, 1 millisecond, 5 milliseconds. It depends on the operating system's implementation. But the idea is the round robin always pauses in between. And I want you to understand that real closely. If I created a robot and I wanted the robot to be like a human being, to have self-awareness, I will have to write the program for that robot in a round robin type situation. In other words, if the robot is a robot that can walk and do a job, I can tell the robot every 1 second, I want you to listen to all your senses. If your senses have picked up any input, I want you to process that input before you continue your operation. So that means if I ask the robot to walk from one location to another, every step it takes 1 second, it checks. Are all my sensors okay? Did I receive any input signal? If no, take the second step. Then check. Did I receive any input signal? Then that's literally how a human being functions. That is why as I'm lecturing, if somebody touches me, the signal is sent to my brain to get my attention. And because I'm paying attention, I can be interrupted. So this is the concept of a preemptive algorithm. As it's working, you can interrupt it so that it switches action and changes operation. A non-preemptive cannot do it. So let's take a look at the non-preemptive. I'll skip right past to the non-preemptive. So here's first come, first serve. And the example is exactly the same. So I don't need to draw the Gantt chart again, but observe what is happening in this Gantt chart. Notice this time, when P1 goes in, it doesn't stop till it finishes. Then it hands over to P2, then to P3, then to P4, then to P5. This is the first come, first serve. So P1 was the first to come, so we handle him first. P2 was the second, then P3, then P4. You can see there's no interruption here. But now when you calculate, the average wait time is 9.6 milliseconds. Compare that now to what we had with the round robin. The round robin, the average wait time was 5.8. 5.8 versus 9.6. Which is better? Which one is better? 5.8. So the lower the number, the better, because less waiting. So you can see that. Then, if we take a look at the turnaround time for the first come, first serve, 13.1 milliseconds compared to 9.6. Which is better? 9.6. So effectively, in this scenario, if we compare first come, first serve with round robin, which is better? Round robin is better, more efficient. Now, let's take a look at shortest job first. The nature of the shortest job first is very similar to the first come, first serve, except that we do the shortest job first. So that's like in a restaurant, and that's actually how restaurants operate. They typically do shortest job first. So if 10 people came and ordered at roughly the same time, they will start with the simple orders before they go to the complicated orders. So this is what it will then look like. And here you can see of the jobs, we look at the table, the process table. P1 needs 10 milliseconds. That's a lot. P2 needs 1. P4 also need 1. So P2 and P4 are the ones with the shortest jobs. So if you have a situation where two jobs have the same value, what do? You take the first one that came. So that's why we begin with P2, then we do P4. So you can see here in the Gantt chart, we do P2, then P4. Then the next guy after that is P3 with a 2 millisecond burst time. So we do P3. And then after that, we do P5 and then P1. But you can again see no interruptions in between. So by just simply rearranging it, now we calculate the wait time. Look at how much wait time we have. 3.2 milliseconds. Compare that to 5.8 and 9.6. So this one now takes the cake. But you will notice that this guy is not the fairest. Because the first guy to come is the last guy to go out. The second to the last guy to come is the second. It's not really fair and balanced. But it's efficient. And if you look at the turnaround time, again, it's lower than all the previous ones. It's 7 milliseconds compared to 9.6 and 13. So in terms of efficiency, in this case, the shortest job takes the cake. But it's not fair, but it's efficient. So I want you to also note, please listen, as your computer is performing actions, this list will keep on growing longer. As a restaurant is open, when the first 10 customers comes and we begin to deal with them, more customers will be coming later and be placing orders. So as they're placing those orders, we have to be rearranging. I want you to imagine this restaurant is doing shortest job first. So it keeps rearranging. So let's say this P1 guy, he has 10 minutes to prep his food. At the time we begin prepping, before we begin prepping his food, another guy comes with a shorter prep for food. We will delay P1. Another guy after that comes, we delay P1. Another guy, another guy, another guy. There's a potential P1 will never get serviced. This is a situation called starvation. So shortest job first, even though it looks like it has good utility, it can lead to a condition called starvation where a process never gets to run because other process keeps running before it because of the nature of the algorithm. Is that clear to everybody? This list from P1 to P5 is not static. As our program, as our computer is running, more processes will be added. And if more processes are added and we insist on doing the shortest job first, the long jobs may never, ever, ever get done, which leads to a condition called starvation. Now, there's a last algorithm called priority. This is the last thing we're doing today, then you can go rest. The priority-based algorithm, like the name suggests, it runs the most important task first. So here's the same set of values, but in this case, we have a new column called priority. In this priority column, we have a priority number. There are two styles of priority. There's what we call high priority and low priority. So for high priority, it means the greater the number. So if I have a priority 5, 5 is greater than 4, and 4 is greater than 3, and 3 is greater than 2, and 2 is greater than 1. So if a process has priority 5, in a high priority system, 5 is more important than a priority 4. Other systems use what we call a low priority system. In that case, 1 will be greater than 2, and 2 will be greater than 3, and 3 will be greater than 4, and 4 will be greater than 5, and so on. By default, if you are not told, you need to assume high priority. If the system is running low priority, the question will tell you that this system is running low priority. So in this case, you can see here, we've not been told anything, so we will assume high priority. So if you look at the priority numbers, which one has the highest priority number? You can see here, P4 has the highest priority of 4. So P4 runs first. Then next priority is 3, which is P1. So P1 then runs. Then next is 2. So P5 runs. Sorry, P3, then P5. Now, between P5 and P2, note that P2 and Okay, yeah. So from P3, P3 has a priority of 3. From 3, the next priority is 2, so P5, and then finally priority of 1, P2. So just by rearranging, we get these values. 8.6 for wait time and 12.4 for turnaround time, yes? For P1 and what? Yes, for P1 and P3, they have the same priority. So we take the first come, first serve in that case. That's why we go with P1 before we go with P3. And that's that. So in your examinations, or rather your second test, these are some of the type of questions that you'll be dealing with. You'll be given a process table and you'll be asked to evaluate based on a particular algorithm, generate a result. You might be asked for the definition or the explanation of a process. You might be asked if a state transition is possible. You might be asked the different types of states that a process can go through and things of that sort. Very simple, nothing complicated, nothing different. So we've taken a look at the scheduling algorithms. So remember, the overall topic is called CPU scheduling, but CPU scheduling is under process control management, which is a fundamental function of the operating system. So in process control management, we started off first by understanding what a process is and what a thread is. Then we transitioned into seeing how operating systems manage processes through an activity called CPU scheduling. The CPU scheduling is just a term that means planning for the CPU or creating a timetable for the CPU. And to create this timetable is just a system to decide which process goes next. When computer scientists are developing these systems, they implement algorithms to it. So we looked at the two different types of algorithms, which is preemptive and non-preemptive. So in the preemptive, we looked at round robin. In the non-preemptive, we looked at first come, first serve, shortest job first, and priority. Now I'm just going to step back to the preemptive where we have multi-level queue and multi-level feedback queue. I'm just going to explain this. No calculation for this one. So for the multi-level queue is a system that has more than one queue. Imagine your bus. If you take the Appet school bus, the bus has just one queue. So you enter. But the bank can have 3 queues. So that's why when you get in, the security guy asks you, what do you want? If you want to do withdrawal, separate queue. You want to do deposit, separate queue. General inquiry, separate queue. So they have 3 queues there. So that's a multi-queue. So a multi-level queue is a situation where you don't have one queue, but you have multiple queues. And in between those queues, one is higher priority than the other. So you have, it's like at the airport. You have the VIP, the business, you have the first class, then the business class, then the let my people go class, and the ordinary Joe, economy class. So you will see when they're loading the plane, they say first class first, then business, then economy class. So this is the same thing that some operating systems do. Windows does multi-level feedback queue. So with the multi-level, you can see the first queue, the VIP queue, is for system processes. So anything that the operating system says is more important. The CPU will concentrate first on that before doing what you want. Second, interactive processes. Third, editing processes. Fourth, batch processes. Student processes means here user processes. So your user processes are at the end of the list. So this is a priority-based queue, but there are 5 queues. Now, the problem with this queue is that sometimes, because the higher priority queue has higher priority, the lower queues may never get service. Imagine a flight that has so many first-class passengers. The economy class guy will never get into the plane if it's based on like a first come, first served based on priority. That's another situation of starvation. So to avoid that problem, the engineers developed an advanced form of the feedback queue, of the multi-level queue, which is the multi-level feedback queue. The only difference between the two is now, if a process is in a lower priority queue and it stays a very long time there, we upgrade it to one level. If it still doesn't get CPU time, we upgrade it another level. That is why you have these lines coming from top to bottom. We keep upgrading till eventually the guy gets to first class. So the longer you stay, eventually you'll be in first class and you will get CPU time. So this is done to avoid starvation. So this is the algorithm that the Windows operating system uses. Not exactly, but similar to this. You get it? All right. So now we open the floor for any quick questions regarding what we've talked about today. We've talked about process control management, CPU scheduling specifically. Can I get a final thumbs up if everything is clear before we jump into other announcements? People, everybody okay here? No questions? No? Okay. So I'll go ahead and stop the recording. In the next class, we will continue with disk scheduling and file management. So now that the recording has stopped,